Okay, hello everyone. What we're going to do now, now that we've seen how the dot product and the cross product behave, and we've seen we're starting to get more and more comfortable with vectors, um, we want to start extending this to um, getting a grip on understanding the algebra of geometric objects in three-dimensional space. So for example, we want to look at finding equations for lines and planes in three-dimensional space. And so first, let's lead off with a question here. That would be like, when are, so here's a question. When are two vectors, say u and v, when are they parallel? Well, clearly we know they're parallel when a line in the direction of u and v, two lines never intersect. Then we would say, okay, well, these two lines are parallel. So then we'll say that these vectors are parallel. So here could be like L1, and we have some other line L2. And we say, okay, these vectors are parallel if the lines defined in the direction of these vectors are parallel. Okay, so we know what a geometric idea of parallel, right? If they're not, if they intersect somewhere, we say they're skew. Okay, but we can be a little more specific about when the vectors are parallel. We say the vectors are parallel when u and v have the same direction or opposite direction. Well, for two vectors to have the same or opposite direction, they have to be, one has to be a scalar multiple of the other. So what this here means is that u equals k times v for some k and r. Okay, so we're saying two vectors are parallel. Like here's u, and say here's v, right? The lines formed from the directions are still parallel. So these vectors u and v still are in parallel directions, right? But it may not be, they might not have exactly the same magnitude, right? Or even the same direction for that matter. One direction can be completely opposite of the other vector. And here, and so for the two directions, if the directions are the same, then we can define k to be the magnitude of u over the magnitude of v. This gets us the scalar we want if the directions are opposite, like the picture I've drawn over here, then we can just define k to be negative magnitude of u over the magnitude of v. And we want to use this notion of parallel vectors to be able to come up with using vectors to get Cartesian equations for a line, right? And so let's look here now in 3 dimensions. Here's how we can define an equation for a line. So here's equation for a line. Okay, let's imagine we have some line L passing through the point P, X naught, Y naught, z naught. Okay. Let's let V be a vector that's parallel to L, right? So what we can think of is we take some point that can vary, right? Q, X, Y, Z. Maybe this point Q can vary along the line here because X, Y, and Z are a variable, right? So we vary Q along X, Y, and Z here, and we look at the vectors that we get. And we know these vectors here, this is the vector PQ. These vectors PQ should be parallel to V, right? So PQ is parallel to the vector V. So if we give these things some components here, let's let V be the vector ABC, and then we know what PQ is going to be. PQ is going to be X minus X naught, Y minus Y naught, Z minus Z naught, right? By the definition of a vector between 2 points. You take the second point minus the first component-wise, right? And so how can we find PQ and V parallel? Or what does it mean for PQ to be parallel to V? It means, so this line here means there exists some constant, which we can call T, such that PQ is a scalar multiple of V. So that means PQ equals T times V for some scalar T, right? And writing this out in components, we have X minus X naught, Y minus Y naught, Z minus Z naught is equal to T times V, which is ABC. And so now to get an equation for the line, we want to be able to express, so remember the point P is fixed, the vector V is fixed. The vector that's varying is Q. So we want to express the vector Q by itself, or isolate X, Y, and Z in this equation down here. So let's do that. So we have X, Y, Z minus X naught, Y naught, Z naught here equals T times ABC. We can move the X naught, Y naught, Z naught vector to the right-hand side of the equation. We have X, Y, Z equals T, A, B, C plus X naught, Y naught, Z naught. And this is the vector equation of a line. This is the vector equation of a line because it's still represented in vectors. So we want to be able to express this in standard Cartesian coordinates. So what can we do here? Well, we can simplify the right-hand side a little more and get X, Y, Z equals TA plus X naught, TB plus Y naught, and TC plus Z naught from first scaling the vector ABC and then adding my components together. And if I do this, we get the system that X should be equal to TA plus X naught, Y should be equal to TB plus Y naught, and Z should be equal to TC plus Z naught. These are the parametric equations of a line. Okay, and to be more formal here, when I say the vector equation of a line, what I should really say is vector equation of a line passing through the point x naught, y naught, z naught with direction vector v, right? And so this is the parametric equation of a line passing through the point x naught, y naught, z naught with direction vector v, which is ABC, okay? And so if you have a point that this line passes through and you can find a direction vector, you can find an equation for this line, right? And these up here is the vector representation. This is the parametric representation. There's something called the symmetric representation of an equation of a line. And if you see in each equation here, we can solve for t. So solving for t in the top one would look like what? It would be like t equals x minus x naught over a. But if we solve the second one, you can see we get something like t equals y minus y naught over b. And we could do something for z as well, and we would get the symmetric equations. Right? And so if t, this is all the same variable, we have the same representation for t, means that these are all equal. So we have x minus x naught over a equals y minus y naught over b equals z minus z naught over c. And you can see why this is called a symmetric equation, because there's symmetry going on here between the variables. And this is the third way to represent a line in three-dimensional space, just given a point that it passes through and a direction vector. So let's do an example here. Let's find the vector equation for a line containing points 1, 4, -2, and points, so this will be point P and point Q, which is given by -3, 5, 0. So we need, what do we need? To find this, we need one point and one direction vector. Okay, how are we going to find these? Well, we have two choices for a point. We can pick either P or we can pick Q, right? We know both of these points will be on the line, and we also need a direction vector. So we can find a direction vector. We have two choices. We have PQ or QP. Because if both of these points lie on the line, then the vector between them is in the direction of the line. So we have two choices here as well. So first, let's calculate a vector parallel to L. We can find this by we'll use PQ for example here. So that's going to be -3 minus 1, 5 minus 4, and 0. And it looks like it's going to be 0 minus a -2, so +2, which means that our direction vector PQ is -4, 1, 2. Okay, and then in the formula, this is what we will use for our direction vector, right? Which was ABC. Our direction vector was ABC. So we know now that x, y, z equals t times the direction vector, which we just calculated to be -4, 1, 2, and then plus x naught, y naught, z naught, which is the point we choose, right? We have to choose one point as well. So let's just choose P. So 1, 4, -2. 1, 4, -2. And this is our vector equation for the line. Now, if we wanted to find the parametric equation, so this is vector. If we wanted to find the parametric, then we would just look component-wise and set each component equal. So we know that x is equal to 1 minus 4t, y is equal to 1 plus 4t, and it looks like z is going to be equal to -2 plus 2t. And so here's our parametric equation. And then the symmetric equation is given by, well, you solve for t, right? And when you solve for t, you get, in the first equation, you get x minus 1 over 4. Over -4, sorry. For y, you get y minus 1 over 4. And for z, you get, this is a negative here, so you get z plus 2 over 2. And here's the symmetric. And so really, we want to eliminate the parameter t. So really, you just want everything over here, right? We'll forget about t. Because the reason we set them all equal was to eliminate t and just look at this purely in Cartesian coordinates here. So here's an example for how we can find an equation in vector, parametric, or symmetric form just by given 2 points. So if you were given 2 points that lie on a line, you can find the equation for the line. Next, we can find the distance between a point and a line. Distance between a point and a line. Okay, so let's imagine we have some line L with direction vector v, or for the sake of the picture here, let's say v is in this direction. Let's change it up a little bit. So here's v. Let's say we have a point on the line P, and we take an arbitrary point not on the line, call it M here, and we want the distance. We want this linear distance from a point to the line. Okay, and how you calculate this is imagining here that v and this vector pm starts at p and ends at m, right? Notice that d is going to be the magnitude of pm, but this is the side of a parallelogram spanned by v and pm. And so we know that the area is going to be the magnitude of v times the magnitude of pm sine theta, which is the magnitude of the cross product of the vector pm cross v. Remember in the last video about the cross product, we learned a property of the magnitude is, or a property of the cross product is that the magnitude is an area of this parallelogram here. But we also know that area is base times height, which means that the area given by pm cross v magnitude is the same as the base, which is v, times the height, which is d, right? This length d here. And so we can simply solve and get that d is equal to the magnitude of pm cross v over the magnitude of v. And so this is how we find the distance between a point to a line with point P and direction vector V. So here's our equation. We just take the point, we take a vector starting at P to M, we take their cross product, take the magnitude, divide it by the magnitude of V, and then we're done. And that's going to wrap it up for this video here. In the next video, we'll see how to do similar constructions, but now for equations of a plane instead of just a line. So next video, we'll see in three-dimensional space, say X, Y, Z, and we have some plane here that passes through a handful of points. We want to say, what's the equation of this plane? Just given like 3 points or a handful of vectors or something. So that's what we'll do in the next video.